post-tensioned podium floor design example. This presentation makes you familiar with the application and construction of podium slabs. You learn the design steps of podium floors by way of a detailed numerical example that is included in this presentation. Find out what are the guidelines for sizing the podium slab, dimensions, and then how to apply the code requirements that must be satisfied for sizing and material strength of podium floors. Finally, obtain hands-on knowledge of detailing requirements of podium floors. Here on the right, I have example of a construction where podium floor is used. Podium slabs are uppermost level of concrete frames that support several stories of often light framing. Here in the image at the right, you see wood framing on the top, concrete below. The podium slab that we are going to discuss today is the separation between the lower part of that is concrete and the upper part, which is wood construction. One significant feature of the podium slabs is that their support arrangement and structural system differs from the typically multi-level light framing they support. Column lines, wall lines above do not generally line up with the supports below. So you end up with a lot of concentrated loads resting not necessarily on supports of the podium, but somewhere in the span. The supports from the superstructure do not generally line up with those of the podium. The primary reason for the difference in the support layout of the podium slab and the structure above is the different occupancy designations. Above the occupancy in the image is residential. Below the occupancy is parking structure. The requirements for parking as far as the spacing of columns are concerned are different from that above. And that is why the columns do not necessarily line up. Now, here on the left is an illustration of a construction scheme where below you have a parking structure, above you have a multi-story residential, and on the right is an example. What you see here is all structure above the podium. In this example on the right, the podium is on the ground level, on the street level, and the parking is below street. Above, one level is retail, and then you have residential above it. Here are two typical examples that you find in California. Concrete is below, wood frame is above. Here in the right, below is the concrete below supports parking. On the left, it is commercial. An example of the post-tensioned slab construction is shown on the right. Now, going to the design, the first step is size of the structural members. By that I mean what should be the column size, what should be the slab thickness, what should be the span, and so on. Next two, we define the load on the podium slab. And third, we select the structural system. I will go through this in detail, what I mean by structural system. I really mean whether it's a two-way system or a one-way system. I will go through that in detail shortly. Next, number 4, we check the sizing adequacy of the structural members, and we do a punching shear check. In other words, we check to make sure that the dimensions we have selected are amenable to a design meeting the code. Then we go through the general check. You make a computer model for integrity, connectivity of the analysis model. What I mean here, and I will walk you through, is to make sure that the computer model that we have made to represent the structure is valid. And here I have it. We validate the computer model. 7, we check the adequacy of the podium thickness based on live load deflection. Next, before moving forward to design of reinforcement and post-tensioning and so on, we check the sizes. We check really the thickness of the podium slab to make sure that the material selected and the thickness can lead to a design that meets the code requirements. Then we do a serviceability check. That's a requirement of the code. We follow that by safety check. That is the next requirement. And finally, the third requirement is check the member for safety and cracking at transfer of pre-stressing under jacking force. And we conclude it by detailing. Number 1 is sizing of the structural member, making sure that the sizes of a column and the slab are adequate. Slab thickness depends on the number of levels that are supported by the podium slab. Obviously, the more load on it, the larger will be the slab thickness. For typical arrangement and residential or office occupancy, the recommended initial selection of slab thickness is span over 40 if the podium slab supports 2 levels above it, and columns could then work if they are around 14 inches. If there are 3 levels supported, the thickness of the slab is recommended to be span over 38. Column size 16 inches. If 4 levels are supported, then it will be span over 35, and the columns around 16 inches. The example I have selected is shown on the right. It has a slab on grade for parking, and this is the podium dimension on the right. The example is a podium slab over a parking level. The parking level is on grade. The podium slab is supported on interior columns and mostly perimeter walls as shown. The podium slab supports 4 levels of wood framing structure. Over it, we have 4 levels. The detailed dimensions of it are shown in the diagram on the right. For the gravity, the slab is designed for bending and shear. The horizontal forces from earthquake or wind are resisted by the shear walls. Here I have shear walls that take the seismic loads and wind loads. There can also be beams framing with columns, which are not used in this example. In this example, we have shear walls. Plan identifies the walls marked SWL as shear wall that are designated to resist seismic forces. Here, this one is the shear wall 2. This one is not a shear wall. So the design of this will be different from the design of this one. As I just mentioned, not all available walls are considered as a shear wall. We are still selecting initial sizes for the example. Slab thickness in this example 11 inches, balconies 9.5 inches. It has, I believe, 2 balconies. Columns 12 inch by 18 inches, walls 8-inch thick, foundation 10-inch slab, uniform thickness. Perimeter of the foundation will be 24-inch wide and 18 inches deep. Column base below foundation will be a pad, 60 by 60 inch pad, 18 inches thick. Now the following initial dimensions are selected. Here below I have the summary of the selection. For concrete, its weight. For the podium slab, the strength, modulus of elasticity, creep coefficient. I use the creep coefficient for deflection, long-term deflection, and columns and walls have 5,000 psi, and the modulus of elasticity, and so on. For the mat foundation, the concrete strength I have selected is 5,000 psi, again modulus of elasticity, and so on. Then we come to soil support. I have selected 200 pound per cubic inch. It's modulus, bulk modulus, and I have selected a friction coefficient of 0.4. This is to resist the seismic horizontal forces, and soil pressure 2,000 pound per square foot allowable. For gravity, axial on the soil 2.6 KSI. Now we are still in sizing of the members before going to the design, and I write the summary of what was selected here in this image that I just closed. Now we move forward with the gravity design first. I have the dimensions given in the previous slide. Here I have the load. The load is summarized on the table on the right. The dead load is based on the slab thickness, In addition, there will be a partition load. The live load is listed here, and the live load is reduced. The code permits reduction of live load, ASCE 7 reduction of live load, if the live load is spread over a minimum area. So in summary, I will design the slab for dead load this much, and the live load 130 pounds per square foot. Next, we come to the selection of the structural system. This is the podium. Before designing it, I have to select the boundary conditions and decide how the load is going to be carried. I have assumed hinge and roller support at selected connections. The columns from the top, I have assumed hinge. The wall from the top, I have assumed hinge support. When it comes to support of the podium slab itself, I have assumed the shear walls to be rigidly connected to the podium, but the non-shear walls are assumed to be on rollers, so the horizontal force will not be taken by these shear walls. When it comes to the columns, I have assumed all the columns hinge at the top and hinge at the bottom for the both gravity and the horizontal forces. Assume hinge and roller support at selected connections as shown in the image. Column to slab is assumed hinged. No shear walls, non-shear walls assumed with no shear transfer. No shear transfer here. Now, I want to make a comment on the previous slide before moving forward. Maybe the comment comes later, and that is assuming a hinge is acceptable in design and is safe, even though in construction there may be dowels and the member might initially get some bending moment. Maybe I will have a reference later here which I will refer to. First, we check punching shear. Now, the objective of the punching shear check at this stage is to verify that the size and material selections made are amenable to design meeting ACI requirements. What do I mean? I mean that the dimensions we selected can conclude with a design. We don't want to go through the calculation and halfway through or toward the end find out that the values we selected do not conclude to a code compliant design and we have to redo everything. This we want to avoid. For that reason, we do punching shear first. ACI imposes an upper bound limit for punching shear demand. If punching shear demand exceeds the maximum allowable value, the design parameters must be modified. You have to restart. We don't want to do that. So in order to avoid abandoning the interim design effort, the maximum shear demand is checked to be within allowable values. How do we do that? The shear demand has the maximum value given here. If the shear demand exceeds the maximum allowable value, the assumed parameters of design must be modified. Options that are open to us are increase in column strength, increase in slab thickness, and increase in size of column or provision of column drops. The objective at this stage is to verify the size and material selections to be acceptable. We assume hinge. Detailing the column connection is likely to be different from assumed hinge condition. Your structural drawings may show reinforcement which do not conform with the hinge connection that we assume in design. The assumption of hinge in design and detailing with stiffness or partial stiffness leads to some moment transfer, but the design will be safe. What I'm saying is that in reality, there could be some moment taken by the connection. But the consequence of that transfer does not impact the safety of the structure that is the target of design. Concrete slab design, that is the argument for it, is based on a ductile system allowing redistribution. In plastic theory of structural analysis for ductile structures, addition of stiffness to a location on a structure does not reduce the ultimate load carrying capacity of the structure. In other words, to assume hinge for design, but detail otherwise with stiffness does not reduce the ultimate load-bearing capacity of the original design. If the design was based on hinge, but the execution was stiffer than hinge, the load-carrying capacity of the structure will not be less than what was designed for. This is one book which gives you the theory of plastic design and the argument for it. There are other books too. So therefore, for this, I go to punching shear to make sure that I do not exceed the maximum allowable. I use the tributary distribution of load to arrive at demand value. I estimate column reaction, calculate the shear stress not to exceed the code value. I revise the parameters as punching shear demand exceeds maximum allowable value. Punching shear will be checked against gravity load only. There will be no moment contribution since column connection is assumed hinged. What do I mean? In checking the punching shear, I do not include wind and seismic because I assume hinge connection. So it is only gravity which will cause punching shear demand. The demand will be checked against maximum allowable value of the code, which is here. I have given the maximum value, maximum allowable. Make sure that it does not exceed this value. Otherwise, select one of the remedial measures stated in the followings to reduce punching shear demand. For design, column to slab connection is assumed hinged, irrespective of connection detailing, which will be in your drawing. I use factored loads to calculate the demand. The factored load is 1.2 dead, 1.6 live, so this is the load per square foot. I select one of the columns. I have selected this column, one of the columns with the largest tributary. This has relatively large tributary, C3. The tributary is 17 by 24.5. The load on it is this much. This is the load per square foot over the area, gives me the total load. The column size is 12 by 18. Slab thickness is known. Effective depth is 8.8 inches. So I calculate the demand stress for the first critical section, which is D over 2 around the column. And that is the demand. Allowable stress is this. I notice that the maximum allowable the demand does not exceed the maximum allowable. So the design is amenable. It is possible to have a design. Next, I generate a model. I use a finite element program. This one has a good, well-proportioned mesh, and I obtained the deflection under self-weight deflection. The objective of the self-weight deflection is to check the displacement shape and visually, based on my engineering judgment, I mean your engineering judgment that do the design, to make sure that the deflected shape under self-weight looks reasonable. Where there is column, where there is support, you have a little deflection. Middle of the span, you have a larger deflection. So it is reasonable as far as engineering judgment and engineering understanding goes. The displacement of the slab conforms to the arrangement of its support. The maximum deflection is a number which is reasonable. At this time, I don't have live load and other loads, but the value, I take it and judge it against my own experience, whether it is reasonable or not. Next, ACI specifies maximum allowable deflection for live load. This is the next important check. Since two-way slab designs based on ACI are assumed not cracked, that is the way ACI works for two-way slabs uncracked. One-way slabs and beams, there may be cracking. If it is uncracked, live load deflection is not influenced by the amount nor the arrangement of pre-stressing. What I want to say is that the live load deflection is based on the diagram on the right, not on the amount of post-tensioning. Post-tensioning, regardless of its magnitude and arrangement, the way ACI views the structure does not impact live load. Live load is based live load deflection is based only on slab thickness and its concrete strength. So for the geometry assumed, live load deflection is the function of slab thickness and concrete strength. I'm repeating myself because I think it's important. Before proceeding further in design, the adequacy of slab thickness and concrete strength selected for a code-compliant design is checked against the live load deflection. The check is carried out for instantaneous deflection under live load. Here, we don't have creep coming into the picture. For live load deflection, it is instantaneous. The allowable code value is span over 360. Total deflection of finished floor shall not exceed this. That is not for live load. This is just a total deflection. This is another requirement, but this applies to the visible condition and sense of comfort. I want to emphasize that this requirement of the code has the reason of visual sense of comfort being one aspect of it, and also function of the floor, malfunction of maybe cabinets and other structures if the deflection is more. So this is the limit, slab over 240. But this is something which we cannot check it at this time, and it is not important. Why is it not important? Because it can be controlled. It can be controlled. So deflection that is likely to result in damage of non-structural brittle elements is span over 480. Now that is something which again is not practical at this time to check, because we do not know when a brittle non-structural element will be installed on the slab. That is not known. And we continue with the deflection check. The live load deflection is this much, which is 0.13. Span length is 30 feet. So deflection over the span is well less than 1/380. So it is acceptable, far less than this value. Hence, slab thickness and concrete strength are acceptable. Design can proceed now for other aspects of it. Next, we go to post-tensioning. Up to now, even though the podium slab was intended and will be post-tensioned, the post-tensioning comes into the picture after we have verified the adequacy of the dimensions and the material property selected. Then we come to post-tensioning. ACI requires that the column-supported slabs to be provided with 125 psi minimum precompression in each of the principal deflections. I want to just digress a little bit. The way ACI defines precompression is based on, I am trying to find a good word for it, is based on, so to say, intuition. It's based on an assumption, not really what pre-compression is in the slab. One of the presentations in the series called post-tensioning design based on intuition explains how ACI calculates the ACI considers the word pre-compression mean. It is not really the stress at neutral axis at centroid of the member. It is something else. But anyway, that is digression. As far as we are concerned, we follow the letter of the code. And the letter of the code, it says 125 in the way I describe it. That's what we will do. So for common construction, this example, we assume 200. 125 is the minimum. We assume 200. Generally, between 200 and 250 are assumed. So I assume 200. When I assume 200, 200 multiplied by the slab thickness for 12 inches gives me this amount of force kips per foot, 26.4 kips per foot. Now, for this amount of pre-compression, I need to select a tendon layout. So I know that the effective stress in pre-stressing steel in strand is about 175 KSI. What I mean is after you stress the tendon, after friction losses, after long-term losses due to creep and shrinkage, whatever, eventually one assumes that you end up with 175 KSI per square inch of strand. So force per tendon will be that 175 times the area of the strand gives me 26.78 kips per strand. So I assume 26.4 that is the force is assumed for design. 26.78 is the force that each strand provides. If I assume an initial force of 26.4, I almost end up, there is a little bit of approximation here, but I assume one strand per foot, 26.4 per foot. So force per tendon will be 26.78. So I have one tendon per foot. Then I have to make an assumption regarding the arrangement of tendons. The common practice in the US is to group them in one direction over the line of columns and arrangement distributed or orthogonal to it in the other direction, grouped in one direction and distributed in the other. Other arrangements are also permitted, but this arrangement is often used because of ease of construction, not because of performance. All of them perform essentially meeting the same, meeting the requirements of the code. So plan shows the arrangement. In the transverse direction, bundles are used at 3 feet on center. 3 strands are bundled together and spaced at 3 feet apart for ease of construction. We have 1 strand per foot, so we bundle 3 of them together and place them 3 feet apart. And we calculate in the other direction, in the banded direction, they will be grouped. I have the profile in this profile here with the flat on the top is line D here, where there is a wall. The tendon goes free over the wall. In the transverse direction, I have a profile like this. To determine the number of strands in the banded direction, I calculate the tributary of it. The tributary of it is 24.5 feet. I assume for ease of calculation 25 feet. Look at grid line D here. Its tributary is 23 feet. I assume 24 tendons. The requirement of 125 psi will be met because I have an average of 200 psi. So I meet the minimum requirement of precompression as ACI understands precompression in the banded direction also. And I analyze to obtain a solution. The diagram here shows the distributed and banded. The serviceability stage of design consists of several checks. After I put the tendons and obtain a solution, I go to serviceability check, and then I go to safety check, and then I go to initial condition check, follow it up by detailing. So the critical one is stress check. The first thing I do is a stress check. 3, ACI does not provide a remedy if the stress check is not met, does not pass. Failure of stress check requires change in design parameters followed by recalculation of stress values. So I have to do stress check first. The code compliance, for code compliance, a representative, which is sometimes called fictitious, tensile stress is calculated and compared with the allowable value. You calculate a number which is representative of a region, and you check that with the code. The computation of representative stress is based on breaking down the slab into design strips. The same design strip also is used for the safety check. So we break the slab into design strips to do stress check, and then we do safety check. In another presentation of this series, the steps to break into design strips are detailed. So the maximum permissible hypothetical tension stress is this. This is due to both total load and sustained load. ACI differentiates between sustained live load and total live load. Sustained live load is the live load that is commonly, in most cases, is likely to be on the member. Total load is the load for which we design. Occasionally, it is possible for the slab to be loaded larger, and that is the total load. So there are allowable stresses. It is the same for tension. For compression, however, the value is different. For sustained load, which is the common, this is the number, and for total, this is the number. By the way, ACI does not tell us or does not specify which fraction of the design live load is to be considered as sustained. It is left to the judgment of the design engineer. So, to follow the concept of ACI, we break the slab into strips, regions in one direction, strips in one direction, and strips in the other direction. Each design strip is subdivided into design sections. We take each of these and break them into design sections like I have shown here. This one here is broken into so many different sections. Figures on the left show the design strips. Figures on the right illustrate the subdivision of each design strip into design sections. We make them into design sections. And then for each of these design sections, we calculate the total demand. For each design section, using the distribution of design values such as moment, shear, and axial action, the integral, the total amount of action, such as total moment, is calculated. We calculate the total area below this curve, and if this one here shows the, let's say, the bending moment, if we have bending moment, we calculate the total moment. If we have shear, we calculate the total shear. Then that total value, which is a single number for each design section, the total demand value, such as total force, is applied to the geometry of the associated design section to arrive at a single stress. So for each design section, we apply the total demand to the total geometry of the section. We obtain a single stress. For hand calculation, it is impractical for real scenarios. It is too complicated. Commercially available computer software is used. In summary, each design section concludes with a single design value for code compliance. Here I have single design values associated for each distribution. For stress check, top fiber stresses for the support line along Y direction are shown here. For this support line, the distribution of stress is this. The maximum value is this. extreme fiber tensile stress is used to meet compliance with the code. Its tension value should meet the code, should not exceed the code. It's mandatory. The load combination generally is taken to be the total load combination. And the sustained is typically not used because the total, for this purpose, for the purpose of stress check, we use total. For deflection, long-term deflection, we use sustained. We get to that later, but right now I concentrate on the total. We check the hypothetical extreme fiber tension against the allowable value. We revise design if the stresses are not met. The serviceability stage of design consists of several checks. The most critical is stress check. 318 does not provide a remedy. I mentioned that before. For stress check, we use a fictitious value and compare it with the code. This is the allowable value. This is again allowable value for total load. ACI does not differentiate between sustained and total when it comes to allowable stresses in stress, in tension. ACI does make a difference for compressive stresses, which is more for sustained, less for allowable. Once we check the stresses and find it acceptable, we go to minimum reinforcement. ACI requires that irrespective of other conditions and other values, you must provide a minimum amount of reinforcement. The minimum rebar is added to our design before safety check. Why? Because in most cases, using ACI, the section design capacity that satisfies the serviceability requirements, we went through the serviceability requirements, satisfies the safety. So we don't have to go through a detailed safety check if serviceability already satisfies the safety also. But there are certain minimum requirements irrespective of all other steps. One is top bars over the support. ACI requires minimum bonded reinforcement over the column region. It is based on the geometry of construction. The minimum is calculated and added. That is something we have to do. Bottom bars in span. Bottom bonded reinforcement in each span is added where the hypothetical extreme fiber tensile stress of the span exceeds the permissible value. Here I have a top, where here is the top. That is always required for the minimum reinforcement. Bottom maybe not, depends on the magnitude of the tension stress at the bottom. So that is the diagram, and looking here over the supports, the minimum area of reinforcement is calculated and added. Bottom reinforcement in a span, in each span is added where the hypothetical extreme fiber tensile stress of the cell respective span exceeds the permissible value. Details of the amount of the minimum rebar are given in the presentation 5 of this series that explains the ACI requirement in detail. So we add the minimum rebar. Then we go to long-term deflection. We are still in serviceability check. Long-term deflection, the control of long-term deflection is primarily for visual effects and proper functioning of installations on the podium slab. Long-term deflection limit is set at span over 240. With a long-term creep of 2, that is ACI value for long-term creep, and sustained live load of 0.3, that means most of the time the live load is a fraction of design live load, and that fraction I have assumed 0.3. I have taken it from the European code. The ACI doesn't give the number. The formula to use is this: 1 instantaneous, 2 long-term times dead PT and sustained load. This is the long-term, plus immediate, the balance of live load, 0.7 L. That should be less than span over 240. The above gives the long-term deflection plus the immediate deflection, which is 0.7 times of live load, considered as sustained. Once the design is satisfying the serviceability and we have put the minimum rebar, we go to safety check, and that is designed for strength. Here I have used a computer software. We add rebar where the demand is not met. There are load combinations in the code. This is the primary load combination. There is another load combination requirement that rarely governs. The one above is mostly the governing. In this combination, we have HYP, the hyperstatic value of pre-stressing. For serviceability, I use PT. For safety, I use hyperstatic. The reason of this switch is because of the method of calculation. Most engineers and ACI uses load balancing, and this is a requirement in load balancing. There are other methods where you do not need to switch between hyperstatic and PT. You can use PT here also. That is explained in another presentation of this series. In each design, for each design strip, the strength demand U is calculated, and the demand is matched against the bending capacity. Now, this diagram on the right explains or describes very clearly the concept. Let us look at the top right. The blue is the capacity based on previous work for the negative moment. The green is the capacity along here for positive moment. The black is the demand calculated in this example for this load combination. I want you to observe that the black region is well within the blue and green. That means for safety of this structure, you need not do a design. You need not, when I say by design, I mean you need not add reinforcement because the existing capacity exceeds the required demand. So for this reason, we go in bending capacity and bending demand consideration. For each design section, the demand is in black in the image and is matched against the existing capacity. Where demand exceeds capacity, rebar is added. In this case, it does not. In the figure, the demand for each support line exceeds the capacity. It is in black. The calculated capacity of the section is based on the post-tensioning, minimum rebar, and the possibly added base reinforcement. In some countries, it is practiced that you put a mesh at the bottom, and also in a country that I know of, you are required to put a mesh on the top. So that mesh, existence of that mesh provides some capacity, which obviously need be accounted for an economic design. Then we go to showing the reinforcement calculated in a diagram like this. Top bar shown on the right, bottom bars shown on the left. This is the outcome of our design so far. The reinforcement in this example was based primarily on minimum requirements. Then we move to detailing. For detailing, one of them is the requirement of ACI for transfer of unbalanced column moment. ACI says if the column moment from the top is this, from the bottom is this, and there is a difference between the moment at the top connection and the moment at the bottom connection, this difference obviously has to be resisted by the slab. So the connection of the columns to the slab is assumed hinged in this case. Because we assumed hinged, the hinge assumption results in zero moment transfer between the column and slab. Hence, special reinforcement detailing to account for transfer of column moment does not apply. If column slab connection is not hinged, well, in our case it was hinged, there will be moment transfer between the column connection and the slab. The moment transfer is the difference between this and this. The slab must be checked to have adequate reinforcement positioned in the slab within a narrow band over the column to resist the column moment transfer. The moment that is transferred to the slab, first, the slab already has that moment in it. I mean, the moment calculated for the slab includes, I want to repeat, the program you use Even you use hand calculation, the moment that you obtain from your calculation at the face of the column in the slab already includes the unbalanced moment, and the reinforcement for which you design the slab already includes the reinforcement necessary for transfer of unbalanced moment. So what is it that the code wants? The code says the fraction or the part which is associated with this unbalance be detailed. It is a detailing. Put the reinforcement which you believe or you calculated or is necessary for this transfer at the location I mean. So in summary, you are not adding rebar. You position the existing rebar where the code tells you. So in the current example, since the column slab connection is assumed hinged, there will be no computed moment transfer. It has to be positioned. Then you do punching shear check. Again, the load combination for punching shear is the same. I have the dead load, I have the live load, I have the hyperstatic reaction for the column, and calculated the demand using this load combination. Columns were assumed hinged. Hence, there will be no computed moment for contribution of punching shear. The value, the maximum value calculated is this much. Concrete provides so much, so the demand is more than what the concrete on its own can take, so we have to provide punching shear reinforcement. We are not worried because we know from the initial check that we did, we are not exceeding the maximum allowable, so we can conclude with a safe design. For punching shear, this is the column dimension, this is the depth of the section, the surface of the first critical section is this much area. Punching shear capacity of concrete selected is this much. Demand exceeds capacity. As I said, it is okay. It is not going to be beyond the maximum. It is within the limit. Demand exceeds, hence punching shear reinforcement is required. We provide punching shear reinforcement, shear studs in this case. After we are done with punching shear, we then go to detailing. The design will be finished by detailing. The detailing is outlined in the presentation 5 of this series for two-way slabs. It includes the following considerations. After the design is done, you go through these steps which are explained in presentation 5. There must be minimum number of bars over the support. You have to have 4 bars minimum. That is given there. There is a requirement for spacing of the minimum bars over the support shall not be more than 12 inches. That is also given in that presentation. Length of the top bars over the support. There is a requirement. Clear span over 3, that is the minimum. Length of the bottom bars were needed. That is a span over 2, again given in that presentation. Spacing of the tendons in one direction, specified somewhere. Now that is I encourage you to also, when you have a moment, look at the presentation, which I think it's one of the presentations, post-tensioning by intuition, which gives more information regarding the required spacing of the tendons. Then minimum number of tendons or minimum amount of non-pre-stress reinforcement, that is also given in the same presentation. Then you have to detail the reinforcement for transfer of unbalanced moments, which I described in the last slide, but the detailing of it again is given in presentation 5, and the maximum spacing of tendons in one direction is also a consideration. So in summary, in design of the Podium slab example, we started with definition and function, sizing of the members, geometry of the example, loading, validate the slab thickness using a punching shear. We then generated an analysis model to visually verify the deflection under self-weight, whether it meets reasonable engineering judgment. Then we obtained a live load deflection, verify the strength of the member and slab thickness. We selected post-tensioning, layout of post-tensioning. We verified the minimum 125 psi by assumption of pre-compression. We obtained solutions for serviceability. We checked the hypothetical tension stress. That was a mandatory requirement. We modified the design where stresses exceeded, but in our case they did not. We then moved to minimum rebar requirement. The code says you have to have a minimum rebar irrespective minimum bonded reinforcement, irrespective of other considerations. Then we check for cracking moments where applicable. In this case, we did not check cracking moment because we used bonded two-way system. If interestingly enough, if you use bonded two-way, no, I'm sorry, let me repeat. We did not check cracking moment capacity because in ACI, if you use unbonded two-way system, tendon layout, you do not need to check for cracking moment. This is opposite to what European code says. European code says if you use bonded reinforcement two-way, you have to check. But that's not, we are not using European code in this example, so we did not check. Then we calculated the hyperstatic moment. We formed the demand moment for safety, which includes the hyperstatic. We checked whether the demand exceeds the capacity, and where it exceeded, in our case it did not, you have to put rebar. And then we went into detailing, which included unbalanced moment, transfer, and then detailing of non-pre-stressed rebar. We checked the initial condition. That means at jacking of strands, we have to make sure that the compressive stresses do not exceed. We wait if they do. we check the tensile stresses. If they do exceed, we either wait or we add rebar. If you add rebar, you do not have to wait. The material from this presentation was extracted from this book. Thank you for listening.